7, 6, 5, 4, 3, 2. Engine start. 1, 0, and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
On March 6, 2009, the Kepler spacecraft rocketed into the night sky on its mission to search for Earth-sized planets in our galaxy.
It was really an exciting experience to be at the launch. I wondered, is it actually going to get into orbit? Is it going to be successful? Will it find planets? Or will it fall into the sea? There's no backup. This is our chance. So it was really an ethereal experience to be there, watch it blaze into the sky, get into orbit, then finally hear its signal. It's okay, it will work.
The spacecraft was designed to search one region of our galaxy for evidence of exoplanets, or planets that are outside our solar system. Using special detectors similar to those found in digital cameras, Kepler will measure the light from many stars and wait for planets to transit in front of them. The system is sensitive enough to gauge the slight dimming of a star's light output when a planet passes between the star and the telescope. Kepler has the unique ability to study the light from an enormous number of stars while gathering very high-quality data about each. Soon after the launch, Kepler was maneuvered into an Earth-trailing orbit around the Sun. 1 month later, the telescope ejected its dust cover, ran its diagnostics, and within a day, the first light test was completed.
We had never actually taken a picture of real stars in the sky. This was the first time. It was going to tell us how the optics were working. Are we in focus? Is the light coming in as we expected? And at 9 o'clock, unexpectedly, we got an email from our engineer saying that the data had been transferred to Ames. So I went into the data den where the big computer monitors are, and I pulled up the image. And watching that image stack itself onto my computer screen was like champagne filling a glass with all of the stars that were there. And I knew that there were 4.5 million stars in our field of view, but seeing them displayed there and really understanding the density of stars that we were looking at, it was beautiful.
The Kepler telescope stares continuously at the same section of the galaxy for a month at a time, measuring the brightness of its target stars. Once a month, it stops viewing for a few hours to turn back towards Earth to transmit its valuable data. The Mission Operations Team at the Laboratory for Atmospheric Space Physics, or LASP, at the University of Colorado in Boulder, is responsible for controlling the Kepler spacecraft and receiving the data downlinks. The data collected at LASP is sent for processing to the Space Telescope Science Institute on the campus of the Johns Hopkins University in Baltimore, Maryland. There, the science data is decoded and processed, then passed along to the Kepler Science Operations Center at NASA Ames Research Center for calibration and final processing.
The Kepler data is 100 times better than the ground-based data that people have seen before. We had to spend a lot of time figuring out how to make the instrument work properly, and we're still spending a lot of time, even now, figuring out how to interpret the data and pull out stuff that's 100 times better than anybody else has done.
After only 43 days of operation, Kepler collected a treasure trove of fascinating data. Some of the first researchers on the Kepler team to benefit from the data were focused on the stars themselves.
Now let me get into the more interesting part.
Their research, called astroseismology, is the effort to understand the structure of stars by studying the unique pulses or quakes that each star generates internally.
What we study is the periods of vibrations in stars. The basic properties that we measure are the size of the star and the age of the star. So if you don't know the size of the star, you actually also don't know the size of the planet. So what we are simply doing is that we use the vibrations to measure the size of stars, and therefore we also know the size of the planets. Kepler will from now on be the mission that you go to when you want the real data. It is a revolution.
An early challenge for the Kepler science team was to validate the quality of their first 43 days of data. They chose to observe a previously discovered exoplanet to prove that their methods would work.
P7b is one of 3 known transiting planets that were discovered in Kepler's field of view before we launched, so of course we put them on our target list. And the first day that we looked at data from Kepler during commissioning, we looked at this star's light curve. The big surprise was that we were able to see the planet going behind the star. So as the planet goes in its orbit towards the backside, it gets brighter because you're seeing more of its sun-warmed face. But then it winks out for about 2 hours as it goes flying behind the star. And the amazing thing is that this drop in brightness of this secondary occultation is only 100 parts per million. But 100 parts per million is a magic number because that's the size of the drop in brightness that you expect for an Earth-sized planet transiting or crossing the face of a sun-sized star.
Several ground observatories around the globe are partnering with the Kepler mission to provide independent confirmations about planetary transits of stars. Kepler detects changes in brightness of many stars that appear to have the signature of a planetary transit. Often, these are later found to be something else, such as a smaller star eclipsing a larger one. The ground observatories help to confirm actual planets from these false positive readings.
The Keck telescope in Hawaii is crucial for Kepler. It does 2 things. It verifies the existence of the planets by looking for the wobble of the host star, yanked gravitationally by the planet, and it allows us to measure the mass of the planet, the bulk mass, by how much the star wobbles. Verifying planets, getting their masses, and hence their densities, is a key part of the Kepler project.
This validation is critical to the process of identifying new planets, such as the Kepler team's first discovery of 5 exoplanets announced at the end of 2009.
The discovery of these 5 planets, 4 of them were Jovian-like, that is big gas giants with densities that were surprising, all the way from water, that to styrofoam, a real surprise. But one of them was a planet very much like Neptune, probably rocky inside with an atmosphere. And so this was a very interesting planet, and a planet very close to its star, yet it didn't bloat like the Jupiter-like planets. So again, a lot of information about the structure of these extrasolar planets that will help us understand those planets and our own.
By June of 2010, the Kepler team had identified between 300 to 700 planet candidates. They released a data set containing about 300 of these possible planets to their research partners around the world to help accelerate their search.
Kepler is revolutionizing the field of exoplanet science. For the first time, a large number of planet candidates can be studied using extremely high-quality data. We're talking about hundreds and hundreds of planets using the best data we have ever seen here on Earth. This will lead to the discovery of many, many new exoplanets and a better understanding of the types of star systems and planets out there. What I find most fascinating is that Kepler is making discoveries of phenomena that we have never before witnessed.
As the team continued to analyze their data, they found a system with multiple planets orbiting a single star. This important discovery was announced in August of 2010.
Kepler 9 is a very special system because it's the first time that anybody has detected a system of planets where multiple planets are transiting or crossing the face of their stars. Moreover, we found a 3rd planet, much smaller, in a much tighter orbit, 1.6 days. It's 1.6 Earth radii, making it a super Earth. So we find 2 Saturn-sized planets and 1 super Earth-sized planet. It represents Kepler's first super Earth-sized planet, as well as the first discovery of multiple transiting planets in one system.
As they continued to process new data and refine their existing data, the Kepler team made perhaps their most important discovery yet.
By January of 2011, Kepler reached another major milestone, which was the announcement of the discovery of its first rocky planet, Kepler 10b. This planet is only slightly larger than the Earth, 1.4 times the radius of the Earth, and about 4.5 times as massive as the Earth. But what's really exciting about this planet discovery is that the average density unquestionably says that this is a rocky world. And it's the first such world that is unquestionably rocky.
Kepler continues to stare at the stars as it watches for shadows in transit. These shadows will hold the key to a wealth of new discoveries that the Kepler team hopes will answer the question, are Earths common or rare in our galaxy? And the Kepler Space Telescope is the right tool at the right time to finally answer that question.